So there are some criterion to control this kind of service, not just by try and error.
Well, no, it's not only by trial and error. It's not only by trial and error. As I mentioned, there have been years of many scientists, many researchers working only on gauges. What they found out, one they found out by thinking a lot, is called the maximal slicing. And you can prove with theorems that this will avoid the singularity. Indeed. Yeah. So there is mathematical proof that, for example, this type of gauge will save you from the singularity.
But it's not true for all time. I think the very daytime I still have, we hit the singularity.
No, this is just coordinate time. So coordinate time can take 2 events.
Right.
And still it won't hit the singularity.
Okay. Yeah. So in principle, this gauge condition will allow you to make simulation running forever. In principle. Then of course numerical error accumulates. It's a different story. In principle. Right. So, and however,
yeah, the real space-time singularity.
Okay.
You are talking about the physical singularity.
Yes.
So do we need to take care of coordinates?
Well, you hopefully you choose coordinates where there is no singularity, except for physical singularity.
Okay.
It's of course you should start from that type of coordinates. Otherwise, you have a problem from the beginning. Okay. So this is what we in principle want. However, it's almost impossible to use because it takes a lot of computations. It's an elliptic equation, and solving it many times, every time steps, it's too long. It would make computations in practice impossible. So, after more studies, researchers found that the solution is to determine the lapse and shift with dynamic equations. So they are not fixed to fixed numbers. They are not fixed to the elliptic equations, but they are evolved in time. In practice, the gauges change at every time. Okay? The gauges follow their own evolution equations, and some of them, the successful ones, are called the Bonham-Stoll slicing. They have this shape. Again, you don't need to memorize this. Just for completeness is there, and they are evolved and they do the job. That's what I would like you to remember. And they are used in all codes. This is mostly for the shift, lapse evolution. And here is an example of what goes wrong if you don't choose a good shift condition. For example, if you set the shift to 0 and you're simulating a black hole, this is actual data from some old simulation. You will see that, and this is the metric in the radial direction. You will see that in different colors at different times. And so you see that the metric becomes bigger and bigger as time goes on. And the gradients of the metric becomes steeper and steeper. And again, computer code algorithms are not happy with steep gradients very often, right? So after a while, this simulation crashed. And also physically, it's related to the physics, it's quite challenging, because if the metric is very big, it means that 2 points that are very close on 2 grid points that are very close, physically, they are very far apart, which as a minimum gives you very, very low resolution. Okay? So if having big elements in the metric is a problem. But if you choose some better shift conditions, you can control it much more. And the better shift conditions are, for example, these called gamma drivers. Again, these are evolved in time. These are partial differential equations evolved in time. And gamma driver is a family of these conditions. Some of them are called non-plus-log conditions. And again, they're used in every code nowadays. And yeah. This? Okay. Okay. Sorry. That will come later. I should have mentioned who was asking. Okay. This is an auxiliary quantity that comes in next slide. I don't want to anticipate too much. All right. So other questions up to here?
Do you have some rationale how to introduce this gamma?
Do you have
some rationale or some reasoning?
Reasoning? Oh, yes, I do. Just a few slides later, okay? Or, well, let's see if it's later or tomorrow. But, yeah, it's another variable, okay? It's another variable that we need to make simulations. In looking at this equation, it's not so important. Okay? Just know that there are these type of equations. And the details we will find out later, or it's in a textbook. After you've understood the basic principles, probably you can quickly find the reference in the reference of all the details. Other questions? All right. So I've been speaking for an hour. So in order to make this all a little less boring, let me wake you up with a little about this hands-on session. Okay? Then there is probably time to go back and go and talk more about the theory today, or anyway, we'll talk about the theory tomorrow. Because the hands-on session requires some preparation. We cannot really start it on one day and finish it on one day, because it takes time to download, it takes time to compile it and so on. Okay? So that's why I think it's better to do it a bit every day. But before that, please raise your hand who has a laptop here to use it for the. Okay, so maybe only 1 in 4 or something like that. So if those who don't have a laptop, if you're interested, I think it's enough if you sit next to someone with a laptop. It can, one types the comments and the other look. It's very nice. Oh, yeah, you don't need to move yet, but maybe next time. And also those of you who have laptops, do you have a Unix-like system, namely a Linux operating system or a Mac OS? Anyone who does not have a Unix-like system? You all have. Okay, good. And can you please raise your hand if you have an OS, Mac OS system? Mac OS system, 1, 2, 3, 4, 5, 6, 7, okay. And the rest you have a Linux system, right? Okay. So it seems it can be done. Also, how many of you had experience with coding? C coding and Fortran coding? Can you raise your hand? C and Fortran? Okay, also not so many. Okay, fine. And who of you has experience with other languages like Python or Perl? Can you raise your hand? Okay. You? Okay. What about using scripts and Unix commands in general? Are you all familiar, you with laptops, are you all familiar with using Unix commands and scripts? Yes? Yes? Can you raise your hand if you're familiar? Only one person? Okay, good. I will get some help from you. Okay, So, the first, okay, I will have to give you some assignment to do by tomorrow. Otherwise, we cannot even start the hands-on session. So, you have to have compilers, Fortran and C compilers installed on your Unix-like partition, Unix-like machine, okay? So, they're free, available. Is there anyone who does not have C and Fortran compiler? Raise your hand if you don't have. Okay, please install. Please install. Also, those of you who have the Mac OS, are you familiar with Mac ports for installing software? If you're not familiar with Mac ports, please raise your hand. Okay, one person. What do you use for installing packages on your Mac?
I have no idea.
Okay. As far as I know, there are fundamentally two options. One is Mac port and the other is Homebrew. And I think I will mostly addressing Mac ports. So if you want, try to install Mac ports on your lab. It's useful. Okay. So, before going on with the theory, let me introduce to you this. Okay. So what we will be using is called the Einstein Toolkit. Einstein Toolkit, EinsteinToolkit.org, is a community-driven software that provides tools and the support for relativistic astrophysics and gravitational physics. They have, look at the website, and it's community-driven, it's completely freeware, it's supported by grants of NSF and others probably in the US. And what does it include? It includes a code to simulate space-time, so black holes. It includes code for simulating general relativistic, two codes for general relativistic hydrodynamics, and similarly for general relativistic magneto hydrodynamics. This all free. It contains code to generate some initial data, like for neutron stars, or binary neutron stars, or binary black holes. And it contains some analysis code, including horizon finders, for finding horizons for black holes. And it provides computational infrastructure, namely, all what usually a physicist does not want to do in the computer science side of the coding, okay? We want to do more of the physics part. So it does for you almost for free, parallelization. Namely, you can write your code into the Einstein Toolkit. Of course, code is already there, but you can write your own, okay? And the system, well, there is some language in this toolkit, but it's rather a small set of comments that you have to use. And if you do so, your code will be automatically parallelized. You can run on your laptop, and the next day you can run on the supercomputer. Right, this thing is called portability. And it provides mesh refinement, adaptive mesh refinement. So you have grids with different resolutions in the same simulation. It provides multi-dimensional input-output, in particular the HDF5 format, useful for visualization. It provides timing reports and memory use reports to profile your code. It provides tools for managing your simulations, so to help you. That's something we do together in a hands-on session. part. So it helps you compile the code, selecting the options and running and checking the output and so on. It provides user support. Of course, that's very important through various channels, but maybe mainly through mailing lists, which are very active mailing lists. Actually, there are weekly phone calls, and everyone is welcome to just call and tell what's your problem or what's your request. And of course, there is a website. And all what is required if you use and publish something with the Einstein Toolkit is to cite a few publications that you find on the web page. Right. So, homework for tomorrow. And tomorrow my lecture is first in the morning. So I'm afraid you'll have to work out tonight. Or you have to have your laptop work out tonight. So let's install the Einstein Toolkit. Not now, but to take note and install it later. Okay. So this is the comments I will show here are based on a tutorial that is on the web page. So if you go to the Einstein Toolkit web page and you look a little around, you will find a simplified tutorial for new users. Maybe I should put this slide somewhere that you can see even after this lecture is over. Okay, but yeah, so for your reference, if you want to look at that page, the comments I use here are slightly modified. Okay, so what you have to do by tomorrow is installing the required software. And this is for the different systems that you might have, but so